So far we have been discussing the DC small signal model of the MOS transistor. Now we can move on to the AC small signal model. It's just an additional, it's an addition to the DC model that we also include the charge storage effects. Basically all the capacitances that come into picture. Okay. So AC model could also have inductors, but at the frequencies that we are interested in, there are no inductors of significance. Okay. So where are the capacitances in a MOS transistor? When the MOSFET is conducting, we have an inversion layer. Okay. So there are two conducting plates, the gate being one and the inversion layer being the other. So there is a capacitance between the gate and the inversion layer. Okay, the gate here and the inversion layer. Now the inversion layer is connected to both the drain and the source. So you can have a capacitance between the drain as well as the source, and how much is apportioned to the drain and how much is apportioned to the source actually depends on the region of operation. Okay, but we make some simplifications regarding that. We assume that there is one model that is true in triode region and another model that is true in the saturation region. Okay, so this is because of the gate oxide capacitance, that is the capacitance between the gate and the inversion layer. Okay. In addition to this, we have a depletion layer everywhere where we have reverse bias junctions. So there is capacitance of this junction, this substrate and the source substrate and the drain. Okay. And additionally, we also have, because the gate does not, there is some extension of gate over the drain and source regions. There is overlap capacitance between the gate and the drain and source regions. Okay. This is simply because of the conducting plates, gate and this N plus region. Okay. So they are in proximity to each other, so there will be some capacitance between them. And there is also a capacitance between the channel region and the bulk region. Now, if you take a PMOS transistor, you start with a P substrate, make an N well, and have the P diffusions to form drain and source. All of the capacitances that I mentioned now also appear here. Additionally, there is also a capacitance between the reverse biased N well and P substrate. Okay. And this can be a large capacitance because the N well can be large. It is usually large. It has to be at least larger than the MOSFET. Okay. And in many cases you have more than one MOSFET in a well. So there can be a substantial capacitance between the N well and P substrate. So this is something you have to take into account, especially when you are not connecting the substrate to VDD. Okay. When you are not connecting the substrate of the PMOS transistor to some fixed potential like VDD, then you have to consider this. Okay. If you connect it to VDD, then the capacitance will be between VDD and ground. It's not as important. It is particularly important when you don't do that and when you connect it to source or something. If you connect it to source, obviously this capacitance will be from the source node to ground. If I draw the symbol of the NMOS, let me call this drain and source. This is across the gate oxide and these are depletion capacitance. Now these capacitances will have an important effect on the AC performance of the circuit. So we have this model CGD, CGS, CDB and CSB. How much is CGD? Basically, it's a distributed capacitance between the gate and the channel. When it's in saturation, there is no channel immediately at the drain end of the device. So you assume that all of this is connected only to the source side and you apportion all of it to the source. Okay? But there will be the overlap part of it. It will just be the overlap capacitance. So how does it depend on the size of the device? It changes only with W, right? Because basically W is the dimension into the page here, and if you go further into the page, you have more capacitance. So CGDO is the capacitance per unit length. And what is CGS? It's a symmetrical device, so whatever is here will be on the other side also. We call it CGSO, but CGSO is assumed to be equal to CGDO. Okay? And what else? If this was a uniform channel, basically if there was a metal plate here, the capacitance would be the capacitance per unit area, which is Cox, times the area of the plate, which is W times L. Okay? But in this case, we have less than, the charge is non-uniformly distributed, and this 2/3 turns out to be the average amount of charge. Okay? And how much is CDB? It's a junction. So there is something that depends on the area of the junction, and there is something that depends on the perimeter of the junction to the sides. Okay? It's just called CJ. This is the junction capacitance per unit area times the area of the drain region plus this is denoted SW to denote side wall. Okay, it's the capacitance per unit length of the same junction times the perimeter of the junction. Okay, if you know the syntax for MOSFET and SPICE, you have to specify the width and length and the number of fingers as well as the perimeter of the drain and the area of the drain, perimeter of the source, area of the source. The reason you need all of this is to calculate the parasitic capacitances. Okay. Now, this is dependent on layout. Now, if you can assume some layout and then calculate this, and that's what you do when you don't have any further information. But when you actually do the layout extractor will find out the exact area and put that into the netlist. Okay. And CSB is similar. It's exactly this. It's the area of the source plus the capacitance per unit length into perimeter of the source. Okay. And these are the capacitances in strong inversion, saturation region. Yeah, actually it is a voltage dependent capacitance. So this is just some parameter that shows how much the capacitance is, and it also depends on the voltage, right? The depletion capacitance of the junction is some basic capacitance divided by something plus the reverse bias voltage. Okay, so that is included in this, but for hand calculation certainly we will not be using any of this. But especially with the low voltage technologies we have today, the amount of variation is also small. Okay, we said this is in saturation region. How do these things change in the triode region? So, especially with zero voltage difference between drain and source, you expect everything to be symmetrical, right? So, and that's the picture we use for all of triode region. So, the channel capacitance is divided equally when lumping it to the drain and the source. Okay. And what happens to these two capacitances? They remain the same because nothing has changed with the junction. So, mainly there are 4 capacitances and the values can be calculated in saturation region and triode region using these models approximately, right. Do you have an idea of relative values of these things? Which of these components is dominant? Is the overlap capacitance more or is this more, and how does CGS compare to CDB and CSB? So, the gate oxide capacitance, because of the thinness of the gate oxide, is the highest. It has a very high density, and it turns out that Cox times WL will be more than the junction capacitance for a given MOSFET. Okay, for a given MOSFET, but the gate source capacitance tends to be higher than the junction capacitances. Okay. But again, because in modern technologies doping has increased a lot, the density of junction capacitance also has increased and it is now somewhat comparable to the gate capacitance. The gate capacitance is still higher, but it's not like 10 times higher or something, maybe it is 2 times higher. In a way, CGS and CGD are intrinsic to the device, at least not the parts that are related to overlap. Once you have a MOSFET, you will certainly have this. Of course, you will also have the other things because you have to make junctions and so on, but the Cox times WL is intrinsic to the operation of the MOSFET. Okay, so that's why it's called the intrinsic capacitance, and all the other things are dependent on how you draw the junctions and how you fabricate them. Okay. To complete the small signal model, we simply add this. These are also this CDB and CSB and so on, especially these are nonlinear, so they are really small signal capacitances. They relate the incremental change in voltage to the incremental change in charge. Okay. So, we add these to the small signal model between the corresponding terminals. Okay. So, the complete model will look like this. What is the effect of these capacitances? So, it will definitely affect something at high frequencies. Okay. And how do we characterize the effect of these capacitances for a single device? Are you aware of any figure of merit for a single device that characterizes the high frequency performance? FT. So, FT actually comes from bipolar transistors. A bipolar transistor is usually characterized by beta, the DC current gain at low frequencies. Now, you extend it to high frequencies and calculate the AC current gain and look at the frequency at which the AC gain becomes 1. Okay. That is known as the transit frequency or FT of the device. So, exactly the same thing is done with the MOSFET also. A small signal AC is applied to the base of a bipolar transistor and the collector is shorted to the emitter, and these are all incremental shorts. It is biased at a certain current level. I am not showing that here. Okay. These are all incremental. So, you calculate IC by IB, you calculate the magnitude of IC by IB over frequency and you plot it. If you do plot it, you will, what do you see? What kind of behavior do you see? So, first order low pass. Okay. And the frequency at which it crosses unity is FT. Okay. So this is what is done for a bipolar transistor, and we do exactly the same for a MOS transistor also. So let's do the same for a MOSFET. We can use the small signal model of a MOSFET to calculate these quantities, and also we connect the bulk to the source, and the GMB source will be disabled. Okay. And this is done typically in the saturation region, that is when you want to use the MOSFET as an amplifier. Okay. This is the source, you short the bulk to the source, and you also short the drain to the source. Okay. And this is grounded, and this is the gate. You apply a current to the gate. So because the bulk source is shorted, this current source is disabled. Disabled meaning it is giving zero incremental current. Okay. And CSB and CDB are also shorted. What we are interested in is in the current out of the drain terminal. Okay. What is the current going to be as a function of frequency? What is ID by IG? So because drain and source are shorted, even GDS doesn't matter. Basically we have only three elements. So what's the current through GM? Okay, GM times VGS. And what is VGS? So the gate current IG flows into CGS and CGD, which are in parallel. Okay. The VGS is IG by S CGS plus CGD. This is VGS times GM. Okay, that's it. So that's all. So ID by IG is GM by S times CGS plus CGD. Is that correct? What else is there? So the current through CGD also flows into the drain. What is that part? This ID consists of two parts. One that flows into GM and another one that flows into CGD. What is the part that flows into CGD? So the current division. This current gets divided into two parts, and it's in the opposite direction also, right? So it is so you again see the right half plane 0 that you saw in the common source amplifier. Okay, that's because of the overlap capacitance or the capacitance CGD. So now what we are interested in is to figure out how this gain behaves when you change the bias conditions of the transistor or when you change the aspect ratio of the transistor. Okay. Now normally what is done is, because CGD is rather small in the saturation region, we completely neglect it and approximate this by GM by S times CGS. Okay. So you neglect CGD compared to CGS, and you approximate it by this quantity. Okay. So we will use the approximate quantity to figure out what happens as you change the bias and as you change the aspect ratio. So how does GM depend on bias? It increases with the current. So what is GM as a function of VGS? What is that? What is the frequency at which the magnitude becomes 1? That is the radian frequency at which. So the FT, which is in hertz, So this is the transit frequency or omega t, okay, and Ft is Gm by 2 pi times Cgs. So we can compute Ft as a function of the bias condition. Ft, as you just mentioned, is mu Cox W by L Vgs minus Vt, okay, and what is Cgs? So 2/3 WL. So it turns out to be some constant times the mobility times the gate overdrive Vgs minus Vt divided by L square. Okay. So first of all, it does not show any dependence on W. Does that make sense? Why does it not show any dependence on W? Yeah. So if you put two transistors in parallel, then the input current increases and the output current also increases, so the current gain doesn't change, right? What else can you tell from this expression? It's proportional to mu. What does that imply? So for if mobility is higher, the Ft is higher, that means that NMOS Ft is higher than PMOS Ft, okay, for a given bias and given length. Then what else? It's inversely proportional to L square. I mean, that's why you actually go and scale technology, right? You want to get a small L, so that in fact, as you reduce the value of L, both Gm increases and the capacitance reduces for a given bias. So it has an inverse L square effect when the square law model is valid. So this means that when you are concerned about speed, you use shorter channel transistors, and it's proportional to Vgs minus Vt. So that means that you have to bias it with a larger Vgs minus Vt to get higher speed. That will have some disadvantages, as we will see later. Okay, we will see the direct trade-off between trying to bias things at a large Vgs Vt. So for some things you want to bias at a large Vgs minus Vt. For some other things you want to bias at a small Vgs minus Vt. Okay. So one quick example is, where would you want a small Vgs minus Vt? You want more swing. The saturation voltage, you need to maintain a minimum of Vgs minus Vt across the drain and source. Okay, and you would like to keep that overhead to as small a value as possible. So in terms of swing limits, you would like to bias things with a small Vgs minus Vt. In terms of speed, you would like to bias at a large Vgs minus Vt. Ft PMOS is less than Ft NMOS. So last time we were discussing operation in the weak inversion of the subthreshold region. Essentially, you keep on reducing Vgs minus Vt. At some point, you will enter the subthreshold region. So this also says that when you go to subthreshold region, it's going to be slower. The expression itself is not valid because it's not in square law anymore. But you do know that as you reduce Vgs minus Vt, Ft goes on reducing. Basically, you need to bias at a large current density. Vgs minus Vt is a measure of current density. Okay. By current density, what I mean is this. ID is mu Cox W by 2L Vgs minus Vt square. So if you keep Vgs minus Vt constant and have a number of devices in parallel, the current just multiplies. So you can think of ID divided by W as a current density. So that is the amount of current per unit micron of width, unit width. So as Vgs minus Vt increases, for unit width you are drawing more and more current through the MOSFET. Okay. So, a large VGS minus VT means a high current density. Okay. So, to get a very high FT, you have to bias it at a very high current density. And FT is inversely proportional to L square. So, short channels for high speed. So, this says that this assumed certain things. What deviations can you have from this expression? Are all these things always true, that FT is directly proportional to mu, FT is proportional to VGS minus VT and inversely proportional to L square? So, in case of velocity saturation, it will be different, right? The proportionality to mu comes in only when you have the velocity is not yet saturated, that is, velocity is still proportional to the field. Okay. So, what happens in velocity saturation? So, this is for something that is not in velocity saturation. Okay. What happens when you have velocity saturation? Okay, so, FT is Gm by Cgs, and what is Gm in velocity saturation? WCox? Vsat, the saturation velocity of the carriers. And Cgs is again the same thing. So, this is 2 pi, sorry. Okay. So, it is not inversely proportional to L square anymore, it is inversely proportional to L. So, this is the reason why when you go to very short channels, you do not get an L square improvement. When you go from, let us say 0.18 to 0.09 micron technology, so you do not get a 4 times increase in speed, you will get something between 2 and 4. So, FT is a measure of speed of a single device. Of course, when we make more complicated circuits, we can evaluate the frequency response and see what the bandwidth is that we can get and work out the trade-offs involved in increasing the bandwidth. But if you did not have anything else, just for evaluating a technology, you can use FT as a measure of an individual device. Okay. Why is this even important? What is Gm by Cgs? You can think of it as a current amplifier, that is, you feed in the current and measure the output current, or you drive it with a voltage and the output is driving a similar device. Okay. Then you get again the same thing, you get Gm by Cgs to be the unity gain frequency, right. So, you apply some voltage and you measure the output voltage, but it is loaded by a similar device, that is the condition. So, in either of these cases, the current gain in this is the same as the voltage gain in this, assuming that there is no CGD. Okay. It's something that is related to the intrinsic behavior of a MOS transistor. So, generally higher FT means that you can make circuits at a higher speed, but these are measured under, this is measured for a single device. So, that limitation you have to keep in mind. So, it does not mean that if FT is 80 gigahertz, you can make 80 gigahertz amplifiers using this technology. Okay. So, usually the specified FT of a given technology is with the maximum possible VGS minus VT and so on. So, you would never in an analog circuit bias with a maximum VGS minus VT. You bias it at some more moderate value where you can get a reasonable swing, etc. Okay. So, those limitations you have to keep in mind, but if you see two technologies, one has much higher FT than another, then it is a good bet that you can make higher speed circuits in this than in the other one. Okay. How would you simulate this? Let us say I want to bias it a given VGS minus VT and I want to simulate FT. How do I do this? Because so far we only took the small signal model and assumed that somehow it is biased to give you certain small signal parameters. I want to bias a transistor. Let me say at a given VGS. I mean, that obviously means a given VGS minus VT. Okay. I have a transistor. Let me not even connect anything. And I have my VGS. And I also want to bias it at a certain VDS. Okay. So how do I connect up the thing so that in either in simulation or in measurement I can measure the FT? Is the question clear? I want to get a full picture including the bias arrangement and the signal injection into the gate. Okay. So in large signal it should have a gate source voltage equal to VGS and a drain source voltage equal to VDS. And in small signal I should get this picture. Okay. This is going into the gate and the drain is incrementally shorted. Initially we will assume a floating source, although they are difficult to find. Okay. Then what do I do with VGS? So the alternative was if series doesn't work, you put it in parallel, right? This is what you wanted, or you wanted a capacitor also here? Okay. So what will this do? Okay. Capacitor. So what, where will the current flow? Huh? Yeah, it will be shorted. Inductor in series with VGS. Okay, perfect. So we can connect an inductor or a resistor because there is no DC flowing through it. We can safely connect a resistor also, right? What will be the value of the inductor and the capacitor? So first of all, I have to say, let's say I want to measure the frequency response from some F min to F max. Okay. Clearly, I cannot measure it at DC because DC this is open. So I have some minimum frequency that is not 0 to some maximum frequency. Maybe there is maximum frequency can be something, I don't know what. So how will I choose L and C? All frequencies of interest, I want all of this current to go here, not go this way. Okay. You have some impedance looking this way and some impedance looking back this way. Okay. If this is Z1, this is C2, the magnitude of Z1 must be much less than magnitude of Z2 over the frequencies of interest. That's what it's at F min that we are interested, right? At F max, if it's true at F min, it will be true at F max because capacitance impedance decreases and inductive impedance increases. This should be much smaller than 2 pi F min times L. So this is how you find the value of L. What about C? What is feeding the capacitor is the current source, right? So I don't care if there is extra drop here. This current will go through the capacitor, isn't it? Whatever the value of capacitance is. If I have some voltage source here or something with a non-infinite input impedance, then I should make sure that all of the current goes here. But in this case, what happens if I put a smaller capacitor or a larger capacitor? Only this voltage will change. Okay. The voltage between this point and this will be I divided by C1 parallel C2. Okay. So actually the capacitance value doesn't matter. Of course, you just put some standard values. When I do simulations, I put 1 farad and go with it. Okay. Also, you can connect a resistance instead of L. And if you do use a resistance, then instead of this, you have R. Okay. So now you think about how to do it. Instead of biasing at a given VGS and VDS, I want to bias at a given VDS and a given ID.